The equation y equals 2x plus 1, that's a pretty easy thing to sketch, right? And if we sketch it, we usually sketch it from left to right, because that's in increasing values of x. Whereas increasing values of theta is always rotational. So we know the graph is going to look something like that. Now, if you type this equation into the calculator in polar form and you hit zoom 6, look how it graphs it. Maybe you don't see all of it. Peter, why would you not see all of it necessarily?
Because it doesn't have the right amount of distances for x. X is bounded.
Or theta is bounded, yeah. So let's go from like negative 5 pi, which would be a little bit further to the left, and let's go 5 pi. I just chose 5 arbitrarily. And let's slow it down a little bit because I want you to see how it sketches it. It's pretty neat. Oh, that still was too fast. Now 5 was probably way too big. It's still graphing. You can interrupt it by hitting the on button, just an FYI. 05. Let's try that. Okay, watch how it graphs it. It's pretty cool. A little piece over here, and then it jumped across to the other side. So like a sine function, it graphs as a piece here, graphs a piece over here, and just jumps back and forth and pieces it all together. And it's still sketching it. So kind of interesting, but it is still the same line. All right, let's go ahead and kind of speed through the rest of these. We're converting from rectangular to polar. This is a pretty easy equation. What does the graph of y equals 4 look like? Horizontal line. Yeah. If I want to convert that to polar, I need to get rid of the y and replace it with either r or a theta. How am I going to do that? R sine of theta, yeah, equals 4. And then if you solve for r, you get 4 over sine of theta, also known as 4 times cosecant of theta. Yeah, so I'm not going to sketch that, but if you graph 4 divided by sine of theta, you'll get that horizontal line. And y equals 4 is pretty simple. Our cosecant theta is not too elaborate. Now this one here, this is kind of a tricky rectangular equation. We can't solve it for y as a single equation. What does this graph as? A circle with a radius of 4. Yeah. So if you know that, you can go straight to the equation. But in general, r squared is equal to x squared plus y squared. So if you want to replace x squared plus y squared with r squared, that's the quickest way to get rid of the x and y. Now, if you solve for r, you're going to either have positive 4 or r equals negative 4. Which one is correct? They actually both are. Yeah. If you start at theta equals 0, positive 4 is going to sketch out like that. If you start at 0 with a radius of negative 4, because it's going to be on the opposite side, it's going to look like this. So it'll just trace out starting at a different point. But they both work. Now, what happens if you didn't see that x squared plus y squared was equal to r squared? And instead, you replace x with r cosine of theta. And you replace y with r sine of theta. Should it work still? Yeah, it should. Let's see why. You get r squared cosine squared plus r squared. So I'm going to factor out the r squared plus sine squared. And when you factor out the r squared, you have that. And what, of course, is cosine squared plus sine squared? That's Papa Pid. It's equal to 1. So you get the same answer. Wow. Ain't math cool? Yeah. All right, so pretty easy going from rectangular to polar. You're just replacing all of your x's and y's with r cosine theta, r sine of theta, respectively. Now, if you're going backwards from polar to rectangular, it's going to be a little bit more fun. What would this graph as? Very quickly, just to review, in polar form. A circle that's off-center, right? X-axis symmetry. And the 2 is the what of the circle? Diameter. So it looks something like that. Good. Now that's going to require 2 separate equations in rectangular form if I want to solve for y. So here's how we're going to put that into rectangular form. Leave r alone first. Don't want to replace r with the square root of x squared plus y squared. That's what it's equal to, but hold off on that. The first thing you want to do, it's kind of a 2-step process. replace any trig function with its definition in terms of x, y, and r. What is cosine of theta in terms of x, y, and r? X over r. Yeah, sine is y over r, cosine is x over r, and tangent's y over x. When you do that, your r's may either divide out or they may combine. In this case, if you multiply both sides by r, you end up with r squared equals 2x. Now, since the r's didn't divide out, now you can replace r squared with x squared plus y squared. Yeah, equals 2x. And then, of course, if you wanted to solve that for y, you'd have 2x minus x squared. You'd have to have two separate equations, plus or minus the square root of 2x minus x squared. One of them would give you the top half of the semicircle and the other one the bottom half. All right, this one over here, theta equals 3 pi fourths. We don't have any r's to replace at all, so I need to get rid of theta and replace it with something that's in terms of x and y. Any ideas? Yeah, it's dealing with tangent. Tangent of theta is y over x. So you can do one of two things. You can actually solve for theta and say it's the inverse tangent of y over x, or it's probably easier maybe just to take the tangent of both sides, and you get tangent of theta equals tangent of 3 pi fourths. That works just as well. And now, of course, you can replace tangent of theta with y over x. And what is tangent of 3 pi fourths? Negative 1. So now if you solve for y, you multiply both sides by x, you get y equals negative x. Do we know what that graph looks like? Yeah, it's that guy. Now let's see why that works for this. If there's no r, remember, as long as the angle is 3 pi fourths, which is over here, you can have a 0 radius or a positive or any negative radius. And so you do get the equation of the line. And then finally here, r equals cosecant of theta. This one has a trig function, so leave r alone. Replace cosecant with what it is in terms of x, y, and r. Cosecant is the reciprocal of sine, so it's r over y. Yeah. Now in this case, what happens to your r's? They actually divide out from both sides, so it takes care of itself. And if you solve for y, then you get y equals 1. And not surprisingly, we get a horizontal line when it's r equals cosecant, because we saw that up above, y equals 4. So it looks like the number in front is going to end up being the y value. All right, so just kind of going back and forth. This really has nothing to do with calculus. Now it's time to BOTC. So we want the slope of a polar equation. Again, we're going to be sketching things by rotating and going a distance from the origin of the pole, but we're still going to be interested in how fast the vertical changes with respect to the horizontal, which is dy dx. Now, when we had parametrics, we had y as a function of t and x as a function of t. We don't have right now y as a function of theta or r or x as a function of theta if we're given the polar equation r equals f of theta. So that is your first step. If you want to figure out dy dx in polar form, you have to use those two equations that we've been using already, x equals r cosine and y equals r sine, to first create a set of parametric equations in terms of theta, where theta is the parameter. Once you have that, then you can fall back on what we did with parametrics. You can take the derivative of y with respect to theta and the derivative of x with respect to theta and divide them out, and you'll end up with your answer, okay? So don't worry about this right here. Don't memorize that. Just tell yourself you're going to be creating two sets of equations, y in terms of theta, x in terms of theta, and then you're doing y prime over x prime, okay? Or, that's what it says. Let me show you what I mean. Find dy dx and the slope of the graph of the polar curve at the given value of theta. So r equals 2 plus 2 sine of theta. It's kind of nice to think about what the curve looks like, although it's not required. 2 plus 2 sine of theta would be the graph of a cart. Yeah, it's a cardioid. And let's see how it quickly traces out. If you just look at your 4 quadrantal angles, it should be enough. So when theta is 0, what is the radius? 2. So we start here, 2. At pi halves, sine of pi halves is 1, so we're up there at 4. And then at pi, we end up with 0 again, so we're two units in that direction. And then at 3 pi halves, we get negative 2 plus 2 is 0. So there's the pole, and then it bounces back. So mine is not quite symmetrical. Let me change that. All right, so you do want it to be somewhat symmetrical. So there's negative 2, and there's 0. So this graph is going to look like this. Comes around there, bounces off the pole, and finishes at 2 pi. So there's what it looks like. So we want to know, what is dy dx at pi halves? Well, now that we know the graph, when we rotate up to pi halves, we're up there. What should the slope be? We have a horizontal tangent line. It should be 0. So let's verify that it is, okay? You're not always going to be able to recognize it like that. It looks like you're going to have 2 more horizontal tangent lines down there, and it looks like there are also 2 vertical tangent lines, which we might be able to find. But to find any of those, we really need to find dy dx. So here's step 1. If r equals 2 plus 2 sine of theta, then x is equal to r cosine of theta, which means x is now equal to 2 plus 2 sine of theta times cosine theta. See that? You're plugging the equation for r into the equation. X equals r cosine theta. So this is from memory, and then you just plug in the radius. Now, we could take the derivative of that, so let's do that first. It's probably easier to find them off to the side. So x prime not of t, that's old habit, x prime of theta. We have created a parametric equation for x in terms of theta. If you distribute the cosine or not, it's up to you. I'm going to leave it factored. It's still going to be a product rule. So the derivative of the first is 0 plus 2 cosine of theta times cosine of theta goes for the ride. And then we're going to have plus the first factor times the derivative of cosine is negative sine. So if you simplify that, you get 2 cosine squared, and then it's going to be minus 2 sine of theta, and then minus 2 sine squared of theta. You'll see that it's going to be a little bit tedious. You're going to have quite a few terms when you do this, but it's not really difficult, okay? So there is my x prime. Now I need to do the same thing for y. Y is equal to r sine of theta. So I'm going to plug in my r, which is, yeah. I distributed this. Yeah. Oh, you could. It's entirely up to you. We'll do that this time. It's just kind of a matter of preference. It's whatever you want to do. I'll do that this go around. Y is equal to r sine of theta in general. That's from memory. And now we plug in our specific equation for r, which is, again, 2 plus 2 sine of theta times sine of theta. So now if you know you're going to take the derivative and you don't want to leave it factored, this is where you could then opt to distribute first. 2 sine of theta plus 2 sine squared of theta. Okay, so now y prime of theta is going to be 2 cosine of theta, and then this by the chain rule will be plus 4 sine of theta times cosine of theta. So it's up to you. It does look like it, at least in this case, it was easier to distribute first, but it would have been an easier derivative anyway because we just had nothing but sines. And on the top one we had sines and cosines. All right, so now I can actually create the equation dy dx is going to be y prime of theta over x prime of theta, right? Now, I don't think I want to rewrite all that, but at least I can use notability. So if I copy that, it's going to be a lot of information here. Not difficult, just very tedious. So there's dy dx, and then I'll copy this one over here, and I'll put it in there. So there, believe it or not, is the equation that'll give you the slope of the tangent line, y in terms of x, for any value of theta. And now we want to know, what is it at pi halves? Well, we know the answer is 0. Let's verify. So dy dx evaluated at theta equals pi halves. We're going to get, let's see, if I plug it in the top, cosine of pi halves is 0. So I get 0. Plus 4 times sine of pi halves, cosine of pi, that's another 0. All over 0 minus sine of pi halves is 1, so that's 2, minus another 2. So I end up with 0 over negative 4, which does in fact give me 0. Wow, that was a lot of work for something that I kind of already knew the answer to based upon the graph. But at least we can verify and say that it works. Okay, the other thing that you're going to have to do is something very similar to what we did with implicit differentiation. You might be asked not to evaluate at a point. You might be asked to find where there are horizontal and vertical tangents. What would that involve? Well, it would involve everything that we did right here, except when you get to your dy dx, in terms of theta, when is the derivative equal to 0 in fraction form? When the what 0? Numerator. So to find horizontal tangents, you're going to have to set the numerator equal to 0 and then solve for theta. And to figure out where you have vertical tangents, you're going to have to set the denominator equal to 0 and solve. And that is a pre-calc question right there in and of itself, solving trigonometric equations. So let's go ahead and try it again. It's a lot of labor. This is the last one we do. It's a lot of work. It's not difficult. It's just very tedious. Okay, so we'll do this one. Find the points of horizontal and vertical tangency to the graphs of 2 minus 2 cosine theta. Now again, if you want to sketch the graph, just to kind of give yourself an idea of what to expect, this is also the graph of a what? Cardioid. Now this one should have what type of symmetry, X or Y? X. Now it's 2 minus instead of 2 plus. Let's just go ahead and put the 4 points on the quadrantal axes and see how it traces out. When theta is 0, what do we get? Well, cosine of 0 is 1, so I get 2 minus 2 is 0. So this one actually starts off at the pole. That's what the negative does. It starts it off at the pole. And then at pi halves, cosine of pi halves is 0, so now we're up at 2. So it's actually doing this. It's coming out like that. And then when we have theta equaling pi, we end up with 4, because it's 2 minus negative 2. So then it comes around like this. And then you can kind of imagine what it's going to look like. It's going to come down here to negative 2, and then it's going to finish back up at the pole. Now, at the pole, because it's a cardioid, that's a cusp. So at the cusp right there, that's neither a vertical nor a horizontal tangent. If you get rid of that part, that little part from the 3, that's neither a vertical nor a horizontal tangent. So that's going to give you 0 over 0 on the derivative. And remember, you throw those out. So let's count how many horizontal tangents we're going to have. We should have 1 here and 1 in here, right? So you should have 2 horizontal tangents. And how many vertical tangents would you expect? Yeah, 1 over there, 1 over here, and 1 over there. And then there would be one place where the derivative is both 0 in the top and bottom, and that's the cusp at the origin. And we'll throw that one out. So let's get to finding the actual angles. I think I could figure out at least this one here. I think there's a vertical tangent when pi at theta equals pi. The others, I'm not quite so sure. So let's go ahead and create our equations. X is equal to R, which if you want to save a line of writing, there's R cosine of theta. And we'll do these side by side. Y is equal to R sine of theta. You want to distribute first? Did you find that easier last time? Maybe? I'll distribute. Yeah, with the if they're in terms of each other, it's for sure easier. Over here, we haven't tried it this way yet, so let's go ahead and give it a go. We'll distribute first. 2 sine of theta minus 2 sine theta cosine theta. All right, so over here, that's going to be easy, but, well, let's do that one first. So x prime of theta, or just x prime, that's going to be negative 2 sine of theta. And then by the chain rule here, we're going to get a negative 4 cosine of theta to the first times the chain rule. The derivative of cosine of theta is what? Negative sine of theta. So the negative changes the sign in front to a plus. I showed that with a different flavor. So not too bad. Now you can always help yourself if you want. You can use identities. So I don't have to use the product rule over there. What is 2 sine of theta cosine theta? Is that equal to anything? That's sine of 2x or sine of 2 theta. That's the double angle for sine. So let's go ahead and use that. It'll keep us from having to use the product rule, which also keeps us from having two terms. So we'll just call that sine of 2 theta. It's an option. All right, so now we'll find y prime of theta, and we get 2 cosine of theta. And now it's going to be minus, leave a little blank, cosine of 2 theta times the chain rule, a 2. So notice we did change the angle. The angle's now 2 theta, a little bit different. All right, so now if you don't want to create dy dx, here's all you have to say. Let's do the horizontal tangents first. We have horizontal tangents when dy dx equals 0, which is when y prime of theta equals 0, right? It's still kind of like a parametric. We have a horizontal tangent when it's not moving vertically at all. That's when the vertical velocity in this case is 0. But it's the numerator of dy dx. So now we can set, bless you, 2 cosine of theta minus 2 cosine of 2 theta equal to 0. And now we have to solve. Now, unfortunately, what made easy work on the derivative using the identity is now preventing us from solving this. Because remember, in pre-cal, in order to solve something, the angles have to be the same. And I have a theta and a 2 theta. So at least in the intermediate, it was nice to have it as 2 theta. But now we have to expand it using the double angle identity. For cosine, which is what? Yeah, you can do them exclusively in terms of sine or cosine or both. In general, let's come over here. Cosine of 2x is cosine squared minus sine squared. It's like Papa Pid, so that makes it easy to remember, just one thing. But notice, because all I have over here are cosines, let's see if we can write this exclusively in terms of cosine. And this would require now a Papa Pid. If you replace the sine squared with 1 minus cosine squared, a la Papa Pid, you get cosine squared of x minus 1 plus cosine squared of x. And now it ends up being 2 cosine squared of x minus 1. So that would be doing bench work off to the side. That's using two separate identities there, the double angle for cosine and Papa Pid. Go gadget pre-cal. All right, so now we'll import that back in. And I have 2 cosine of 2x minus 1. And so what that does now is it gives me essentially a quadratic. If I expand it out, I get negative 4 cosine squared of x plus 2 cosine. I should use theta, my bad. I'll change them all back to thetas. Plus the 2 cosine theta that was there, and then I have a minus 2 times the negative 1, which is plus 2. I have a quadratic in terms of cosine. What should we do before we try to factor the quadratic? Maybe factor out not just a 2, but maybe a negative 2, because we want the leading coefficient to be a positive number. So that gives me 2 cosine squared of theta minus cosine of theta minus 1 equals 0. And now if you're expected to solve one like this, and this is a lot of pre-cal, it's going to be factorable. So the negative 2 is still there. It's going to factor because 2 is prime. It's going to be a 2 cosine of theta plus or minus something, and a 1 cosine of theta plus or minus something. And then the factor at the back of negative 1 only factors one way, 1 and negative 1. So those have to be 1s. And so now we can just play with the signs. The middle term has to be a negative number, so the larger product, which is your outside in this case, has to be negative. So now just verify. You're going to have a negative 2 cosine on the outside, a positive 1 cosine on the inside. That's a negative cosine. Yeah. All right, so now we can set each factor equal to 0. We don't need to worry about the negative 2 anymore. So either 2 cosine of theta plus 1 equals 0, or cosine of theta minus 1 equals 0. So if I solve for cosine of theta, that's negative 1/2. Over here, I get cosine of theta equals 1. And now it's unit circle time in reverse. From 0 to 2 pi, which is what this thing traces out, where is cosine equal to negative 1/2? pi thirds reference angle, but now I need to be in quadrant 2, so 2 pi thirds, and then also in quadrant 3, which is 4 pi thirds. Yeah, 5 pi thirds is quadrant 4, where it's positive. And then cosine is only equal to 1 at 0. So I have 3 places where we have horizontal tangents. Is that right? Well, notice the 2 pi thirds and the 4 pi thirds. That makes sense because remember, pi thirds is like 60 degrees. So that's like barely off, 30 degrees off the y-axis there, and also down there symmetrically. But notice at 0, it does make the numerator 0, but it will, you'll see, also make the denominator 0. And that gives us, like we said in the beginning, 0 over 0. So we throw it out. So if we knew what the graph was, we were only anticipating 2. It's going to be those 2 right there. And 0 is a cusp. It's not a vertical tangent, nor is it a horizontal tangent.
If we didn't build a graph and put 0 as one answer, it's going to be wrong.
Yes, but I don't think they're going to ask you that because that's a lot of work just to kind of stumble across a wrong answer. They would ask you something like this, like what are the horizontal and the vertical tangents? And so what's going to happen is you're going to come up with 0 in both sets of solutions. And what you realize then is if it shows up both places, you throw it out. So they will expect you to know to do that. But they won't ask you necessarily to do one without doing the other. Or if they did, you wouldn't get one that gives you 0 over 0. All right, so golly, let's do the next one, vertical tangents. It's a lot of work. By the way, you probably wouldn't even be asked to find one like this where you have to use all those identities. This one, vertical tangents, would be more of a fair question. Okay, and you'll see why. If we do vertical tangents, we want dy dx to be infinity, right? Plus or minus, which means dy dx is going to be non-zero over 0. 5 over 0, 10 over 0, those are all infinity. So essentially we're setting x prime of theta equal to 0. Well, did we find x prime of theta? Yeah, it's right there. So it's going to be negative 2 sine of theta plus 4 cosine of theta times sine of theta. And now if you set that equal to 0, this is a much easier equation to solve. So what I can envision if this were a BC test, they would only ask you on this problem to find the vertical tangents and not the horizontal. But we like to do hard stuff, okay? Why is this one easier to solve? There's a common factor, right? Factor out a negative 2 sine of theta, and you're left with just sine of theta minus 2, you're left with, sorry, I sensed the bell. You're left with 1 minus 2 cosine of theta. And now you set them each equal to 0. So sine of theta equals 0, or if you set this factor equal to 0, you get cosine of theta equals positive 1/2. Where is sine equal to 0? At 0 and pi. Now we throw out the 0 because it appeared over here. Anything that shows up both you throw out. And then where is cosine equal to 1/2? Pi thirds and 5 pi thirds. So there's 3 vertical tangents that we are expecting. And notice one of them was over here at pi, and then the other 2 were over here at pi thirds and 5 pi thirds. So that one, in this case, vertical tangents, that's a fair question. Didn't require nearly as much work and 2 fewer identities, okay? So we're done with this section. Not difficult, pretty tedious. You got to remember x equals r cosine theta, y equals r sine of theta. Tomorrow, we'll do polar area. It's one of my very favorites. Polar area. I say tomorrow, that means Saturday. Gosh, the weekend always gets in the way. Oh, man. I guess we'll have